Hello everyone, my name is Sofia Cienfuegos. I'm one of Krista's PhD students, and actually Krista told me to teach you guys about vitamin B2 this time. So today we're going to talk about riboflavin or vitamin B2, and to be completely honest, this is one of the vitamins that you don't talk about or you don't use that often because it's among the B complex. So usually you won't hear that often about riboflavin, but it is actually a very important vitamin, and it's very important to keep in mind its function. So I know that you've been covering some water-soluble vitamins already. The two main types of water-soluble vitamins are vitamin C and vitamin B. But vitamin B is a complex of 8 different vitamins, and they are divided into those with a hematopoietic function, so those that are involved in the formation of red blood cells, and those that their main function is energy release or metabolic pathways in general. So you already talked about vitamin C, that it's found in citrus foods. The function is hydroxylation and reactions. It's basically an antioxidant, and also it could be a pro-oxidant vitamin. It has an important role in colds and cancer and cardiovascular disease, a deficiency, scurvy, and actually, I don't know if you've ever heard about the carnivore diet that's been popular lately. I've heard some cases of people in a carnivore diet developing scurvy because of the low vitamin C in their diets. That was just a parenthesis. And the toxicity could lead to diarrhea and kidney stones. And I know that you also talked about thiamine, that's found in meats and grains. The function is energy transformation, nerve conduction. The deficiency could be Beriberi or Wernicke's syndrome, and there's no established toxicity. So today we're going to talk about riboflavin. And here you have the beautiful structure of a riboflavin. So basically, riboflavin has two main parts. The first part is the flavin part. So it's an isoalloxacin ring. I don't know if I pronounce that correctly. And the second part is a ribitol. And ribitol is a sugar alcohol. Everything that ends in OL, in ol, usually is a sugar alcohol, like xylitol, maltitol, and probably you've heard those from like sugar-free chewing gum or something like that. Flavin means yellow in Latin, and you can realize that you ingested something yellow in your urine when you ingested too much of riboflavin. So actually, when I was just starting to study nutrition a couple of years, well, like 10 years ago, I started taking some supplements for energy. I was like, I need more energy, and I saw these supplements that had a lot of like energy boosting and stuff like that. So I took those supplements, and suddenly my urine started turning like very, very bright yellow, sort of greenish color, and I freaked out a little bit. And then actually, when I was in this sort of class, when I was in undergrad, I learned that it was due to riboflavin in that super energy boosting supplements, because of course riboflavin has an important role in energy release and energy metabolism in general that we'll learn in this lecture. Okay, so riboflavin, the thing that we're going to talk about the most in this lecture, is about the coenzyme forms of riboflavin. So riboflavin as riboflavin, it's just for absorbing it, but for riboflavin to exert its function, it needs to be converted into one of their two coenzyme forms. So the first coenzyme form of riboflavin is FMN, or flavin mononucleotide. And this is flavin mononucleotide. So it's the basic structure of riboflavin that we talked about a couple slides ago, plus a phosphate group. So this is the only thing that gets added into riboflavin, that it transforms the normal vitamin into a cofactor. And the second cofactor form of riboflavin is FAD, or flavin adenine dinucleotide. So This is the basic structure of riboflavin that we talked about. And in order to get transformed into the cofactor FAD, or flavin adenine dinucleotide, it needs to receive or get AMP group added. So when you add an AMP group, it transforms into flavin adenine dinucleotide, the coenzyme form. And when it gets a phosphate group, it gets transformed into flavin mononucleotide form. And we have two main coenzyme forms of this important vitamin. And this part may seem a little confusing with all the chemical structures and everything, but don't get too caught away with the molecules and stuff. Just remember that most vitamins are important to our body because they act as coenzymes. And even though they're really tiny molecules that have a tiny effect on certain pathways, they are so important, because if they're not there, the enzyme cannot work properly and the entire reaction cannot happen as it should. So a coenzyme, as I mentioned, is a substance that activates an enzyme. We have many different enzymes in different parts of our bodies, and those enzymes need some signals to know if they should act or not, if they should perform their activity or not. And a lot of vitamins are basically the keys that tell certain enzymes, you need to act now. You need to transform this thing into this other thing. And riboflavin is a very important, let's say, key for many enzymes in our body. But in order to act as a key, it needs to get transformed into the coenzyme form that we just mentioned. So the enzyme will not be activated until the coenzyme is attached to the enzyme and letting them know that the enzyme should be activated. So here is the vitamin form. Here is the coenzyme form. Just added this little part there. And we show you this to let you know and to make it clear that whenever we talk about the coenzyme form, it's not that we change the vitamin form. It's not that the riboflavin is lost or that it lost its shape or it's broken down. No, the vitamin form is still there. It's like inside of the coenzyme form. The vitamin, riboflavin, gets some other things added on top of the vitamin that makes it transform into a coenzyme, but the actual vitamin is still intact in there. So when riboflavin gets transformed into the coenzyme form, it can bind with the inactive enzyme and then magically activating it. There, activating it. So there are different food sources for riboflavin. Here we'll show you a couple of them. Always in most vitamins you'll see liver very often, because liver is usually the food component with the most amount of minerals and vitamins and nutrients, because of course the liver is such an important organ for all mammals. So here you see that 3.5 ounces of liver has 4.1 milligrams of riboflavin. And actually, the recommended daily intake or daily allowances for riboflavin is around 1.1, 1.3 milligrams. So just 3.5 ounces of liver have more riboflavin than we actually need a day. Also, cereals like fortified grains, fortified cereals also have a good amount of vitamins in there. In this case, riboflavin, 0.45. Milk, a cup of milk has 0.41 milligrams of riboflavin. So the main food sources for riboflavin are both from animal products and also fortified cereals. From animal products, mainly is found in meat, milk, and eggs. And in fortified cereals, we can have about 50% of our needs covered from fortified cereals. Also, it's important to keep in mind that the form of riboflavin that's found in different foods varies. So, Whenever we consume either animal products such as milk or eggs or enriched cereals, riboflavin comes binded with protein or alone, or just riboflavin. But when we consume riboflavin that's found in legumes or vegetables, we actually consume the coenzymatic form of the vitamin. So instead of just having riboflavin, like in animal products or enriched cereals, we have the coenzymes that we just talked about. Flavin mononucleotide or flavin adenine dinucleotide. Sorry, I keep on forgetting that name. Okay, so probably you've already discussed when you talked about vitamin C or thiamine that certain things can decrease the amount of vitamins in a certain food. So certain processes, heat, water, light, and different things can decrease the amount of certain vitamins. So if we, for instance, if we want to eat 3.5 ounces of liver because we really need riboflavin, and we want to grill it. So we want to eat grilled liver for lunch. What's going to happen with the amount of riboflavin there if we grill that piece of liver? Well, actually, riboflavin is very heat stable, or generally heat stable. So because of heat, it's not going to degrade, or we're not going to lose riboflavin because of heat. However, if instead of grilling it, we decide to boil it, and I think that's not that delicious, and boiled liver is like, well, never mind. If we decide to boil our liver, not our liver, the piece of liver that we bought at Mariano's or wherever, we will lose some of that riboflavin because it does leach into water. Because it's a water-soluble vitamin, when it gets into contact with water, it will leach out of the product and we will lose a little bit of riboflavin that way. It doesn't mean that we're gonna get zero riboflavin, we're gonna get some, but some of it is going to lose. So if you want to make sure that you're consuming an adequate amount of riboflavin in that certain food, for example liver, you should avoid boiling in excessive water. About light, if we expose our piece of liver to the sun, then we will lose some riboflavin because it is sensitive to light. So for instance, if you have a certain food that's rich in riboflavin, make sure that you store it in containers where light cannot pass. For instance, milk has a good amount of riboflavin, should always be stored in opaque containers in order to preserve those vitamins and minerals that get altered with light, like riboflavin. And I don't know if you've ever seen like these really fancy new milk containers in Whole Foods that are like glass. They're beautiful, minimalistic, but they're glass, like normal translucent glass. And whenever I look at them, I'm like, I know that there's some vitamins that are getting lost there. For instance, riboflavin. So always try to keep foods that are rich in riboflavin in opaque containers because it does get altered with light exposure. Also, we can find, of course, riboflavin in supplements. We can find riboflavin in its free form, so just the vitamin. We can find it as the coenzyme form, FMN, and they both appear to be somehow well absorbed. And actually, supplements of just riboflavin have very high doses compared to the daily allowances or the recommended daily intake. Remember that the recommended daily intake is 1.1, 1.3. We're going to talk about that later. But if in a supplement there's 100, it's way, way more than what we actually need. But we'll discuss about that later. Okay, so how do we digest vitamin B2 or riboflavin that is found in food that's bounded to proteins? So a couple slides ago, I showed you that riboflavin that is found in animal products or in fortified cereal could be either free or bounded to protein. If it is binded to protein, it's not a big deal because in our stomach we have hydrochloric acid, and this will dissolve these bonds between riboflavin and protein. Because hydrochloric acid is like the first step of protein digestion. So whenever this riboflavin that's binded to protein reaches the stomach, hydrochloric acid will separate those and free riboflavin, and it's in its truest, free, normal, happy form. Now, what happens if instead of eating or consuming riboflavin bounded to protein or free, and we consume the actual coenzyme form? I remember that a couple slides ago I showed you that if we consume it from legumes or certain vegetables, we will consume the coenzyme form instead of the free form. So, if we consume the coenzyme form, we need to get rid of all of those phosphate groups and adenosine groups in order to be able to absorb it into our bodies. So we are not able to absorb the coenzymatic forms of riboflavin. In order to get absorbed, we need to get rid of those extra things that got added to them when that vegetable was basically trying to make it a coenzyme. So if we ingested FAD, then an enzyme that's called FAD pyrophosphatase, that's present in our intestines, will get the one phosphate group and one adenosine group out of the coenzyme, and then FMN phosphatase, that's also present in our intestine, will get rid of that remaining phosphate group, setting our riboflavin free and making it able to be absorbed by our enterocytes. So if we think about this, when we consume the coenzyme form, we need some extra steps in order to free riboflavin to making it absorbable, let's say. And that makes it a little bit more difficult to digest and to absorb. That's why B2 that comes from animal sources, it's better absorbed than those that come from plant sources. Because if it comes from animal sources, it is either free or binded to protein. And if it is binded to protein, just the hydrochloric acid is going to remove that bond. However, if we consume it from legumes or other plant sources in the coenzymatic form, then we need some extra steps and some other enzymes to remove those groups in order to free riboflavin and make it able to be absorbed by our enterocytes. And also there are some minerals such as copper, zinc, and iron that can inhibit absorption of riboflavin a little bit. Also, alcohol, and this is very important, impairs both digestion, absorption, and renal reabsorption of riboflavin. And this is why, we're going to talk about this later, but people with severe alcoholism can have deficiencies of riboflavin. So how does it get absorbed? Basically, it depends if we have a high intake or a high concentration of riboflavin, or if we have a low concentration of riboflavin. So if we ate something with a ton of riboflavin and we have a lot of riboflavin in our lumen or inside of our intestine, then the absorption will be through passive diffusion, so no energy needed. It's just going to passively go inside the enterocyte. However, if we just have a little bit of riboflavin, a little amount of riboflavin in our lumen, then we will need some specific carrier to actively incorporate it to the enterocyte, like a sodium-independent carrier or an energy-dependent carrier. So it's a little bit more difficult to absorb it when we have just a little bit, whereas where we have a ton. How much riboflavin is absorbed? So actually, it's pretty well absorbed compared to other vitamins. 95% is absorbed from food sources or supplements. So most of it will get absorbed. Maximal absorption occurs when your intake is between 20 and 25 milligrams. Remember, the daily intake is around 1.1. So when your intake is about like way higher than the recommended intake, like 20-25. And the peak concentrations of riboflavin in your blood is when your intake is about 20 milligrams. And absorption will decrease or will get sort of saturated when your intake is higher than 25. And actually your body is really good at absorbing vitamin 2, so it can actually absorb up to 25 times its riboflavin needs before absorption decreases. And it's not that absorption stops, it's just that it decreases a little bit from that 95% that we mentioned in the beginning. So riboflavin, we already discussed how it gets absorbed into the enterocyte. So when riboflavin enters the enterocyte, it can either get transformed into the coenzyme form, FMN, or it could just stay as riboflavin. If it stays as riboflavin, then it can get exported to portal blood, and the portal vein will take this riboflavin into the liver, and once it enters the liver, it could get transformed into both of these coenzyme forms, both FMN or FAD. And usually FAD is the predominant form of riboflavin that is found in tissues. So most of it is transformed into FAD rather than FMN, and that's important to keep in mind as well. How do you transport riboflavin in your blood? It's not that riboflavin is just freely swimming in your blood. No, it needs something to transport it into either the liver or other tissues. So there are there's like 3, let's say, Ubers or cars that can move riboflavin to the different tissues. The first one is immunoglobulins. So immunoglobulins can actually bound riboflavin and take it to the different tissues or organs that it needs to be delivered. Also, it can be bounded to albumin, and of course, albumin is like the master Uber in our body. Like, it carries a ton of different things. So there's going to be many vitamins and things and lipids and things that albumin transports. And we also have fibrinogen. I'm not sure if I'm pronouncing this correctly, I'm so sorry, but fibrinogen is also able to transport riboflavin to different tissues and places in our body. Actually, when we see different tissues in our body, we see that there's some riboflavin in different tissues. But mostly it is in our heart, kidney, and liver. However, vitamin B2 or riboflavin is not something that we store. We can have some storage, like a little bit of storage, but we don't actively store it as vitamin D, for instance, or vitamin E, like the more fat-soluble vitamins. This one, the excess basically gets excreted through the urine. So that's why it's not that risky if we over supplement or we take a really high amount of this vitamin. And because we don't store it, or we don't store an important amount of vitamin B2 in our bodies, and also our bodies are not able to produce riboflavin, we need to take it from the diet. We need to consume it. And that is why when for some reason you don't consume the right amount or you don't absorb the right amount, you actually can have deficiencies of this vitamin. We're going to talk about that later. Now, we already discussed how riboflavin is digested, how it is absorbed into the enterocyte in our intestine. We already discussed how it travels in the blood, how it gets to the liver. And now we need to discuss what happens with riboflavin when it gets absorbed into different tissues. So again, similar to what happens in the enterocyte, when there's low concentration, we definitely need a carrier-mediated absorption. So we need something that probably needs energy to get that riboflavin absorbed. But when we have a high concentration or a high amount of riboflavin on that specific tissue, then it just gets absorbed through passive diffusion and without energy, basically. Then, after entering tissues, of course, it's gonna get transformed into its functional forms. So they're gonna add these phosphate groups and these different groups in order to transform this riboflavin into either FMN or FAD, because this is the active form of the vitamin. Remember, the vitamin in itself is useful for absorption, for carrying it through different tissues, but whenever it's inside a certain cell or a certain tissue, then it needs to get transformed into the coenzyme form in order to be working, in order to activate and to do its job, basically. So some important things to remember about riboflavin absorption and transport. When riboflavin is being transformed, it's generally just riboflavin. Riboflavin in its free form, its natural vitamin form. When crossing membranes, different tissues membranes, liver membranes, or any cell membrane, it needs to be in the riboflavin free form as well. But when it is in a certain cell, or we need to store a little bit, we just store a little bit, riboflavin is converted into either FMN or FAD in cells tissues. So why FMN and FAD are important? Why do we need to convert these vitamin, riboflavin, into these two different things? It is because they have very important roles in our body. Mainly, they are oxidizing agents or flavoproteins, and they function as coenzymes in oxidative enzyme systems. This part is where it gets a little bit confusing, but basically what you need to remember about the ability of either FMN and FAD is that they are able to accept a pair of hydrogen atoms. So here in the lower part, you see that in the part where it is in red, the isoalloxacin ring can accept hydrogen atoms, and this is the best thing about this part of this coenzyme. Here it is where it already accepted one hydrogen atom, and now here it accepted two. So it is able to accept two hydrogen atoms, and then when it accepts both of these hydrogen atoms, it forms FMNH2 or FADH2. And these two, you will see them in different metabolic reactions. So what are the functions of these things that I just mentioned? There are many different functions, but the main ones are the decarboxylation of pyruvate, the electron transport chain, and some others. So here, we're gonna talk about the decarboxylation of pyruvate. Don't get scared, this image is awful, it's terrible. The only thing that you need to remember here is that, of course, when we have a glucose molecule, we do some glycolysis in the cytosol of the cell, and then after glycolysis, we have two pyruvates. Those pyruvates, if there's oxygen in that cell, those pyruvates will go inside the mitochondria for further, let's say, broken down. So the first step is the decarboxylation of pyruvate, where you remove a carboxyl group from pyruvate, and then the remaining thing from that reaction can go into the Krebs cycle. We don't need to remember that. And then after the Krebs cycle, to the electron transport chain. So here, in the decarboxylation of pyruvate, that is the metabolic part that integrates glycolysis and the Krebs cycle, there's one fourth step that uses FAD, FADH in order to form NADH plus H. And this thing, NADH plus H, is one of the things that will be used in the electron transport chain. So basically here, our good friend riboflavin, this vitamin that we've been talking, has this tiny effect here that is huge in the rest of the reaction to happen. So whenever we create FADH and NADH plus H, basically NADH plus H, we then use this one for the electron transport chain. Here, I don't know if you can see the pointer, we have NADH, and those hydrogen, get transported outside of the mitochondria, and we just get 2 NAD, and same with FADH2, those hydrogens get, it's part of the electron transport chain. We don't need to go into too much detail. Even for me, it's a little bit confusing, but here we know that this coenzyme and this vitamin is basically doing a crucial role in a very important metabolic pathway, that its end product is ATP, and ATP is energy. So this is the explanation why in that supplement that I took when 10 years ago when I needed energy had riboflavin, because riboflavin has a direct effect in energy production because it's able to release hydrogen ions outside of the mitochondria in the electron transport chain, and many other functions. It's not just that, it's not just in the decarboxylation of pyruvate or the electron transport chain, there are many others. And actually, there are many other reactions where riboflavin is really important, and those reactions are reactions of other vitamins. So it helps other vitamins to exert its function. For instance, the conversion of vitamin B6 that you'll talk about in a couple other lectures to pyridoxalic acid, or retinol to retinoic acid, or the synthesis of the active form of folate, or the synthesis of niacin from tryptophan, or the regulation of glutathione. Sorry, this one is really important as well. And now we already talked about excretion. We already talked about absorption in the lumen of the enterocyte, absorption in the liver, absorption in different tissues. What's the effect that it has on those tissues? And now, of course, we need to talk about how do we get rid of it, how do we excrete it. And we know that this is a water-soluble vitamin, and water-soluble vitamins we're able to excrete them easily on our urine, on our pee. We pee them out, basically. So that's why they're not as dangerous as vitamin E or vitamin D, that if we take too much of those, they will get stored in our body, and there are important toxicities. This one, if we take too much, we just pee it out. So 70% of riboflavin is excreted intact, just how it got absorbed, just riboflavin, not bounded to protein, not converted into something else. And it's filtered by the glomeruli prior to excretion. And just 30% of riboflavin is excreted as metabolized. And this means that that's what it got used or transformed into something else that's metabolites. And these are the three main metabolites: 7-alpha hydroxymethyl riboflavin, 8-alpha sulfonyl riboflavin, and 10-alpha hydroxyethyl riboflavin. And these metabolites arise from tissue degradation of riboflavin. And we also have a little bit of fecal excretion of riboflavin. There is some riboflavin that does not get absorbed in the small intestine, so it reaches our colon and it gets fermented by our bacteria, and the rest of the metabolites are excreted in the feces. So you can have some metabolites of riboflavin in our feces. So we've been talking about the recommended daily allowances of riboflavin. This is in milligrams a day. For infants, it's 0.04, children 0.06, males 1.3, females 1.1, pregnancy a little bit higher, 1.4, and breastfeeding or lactation also a little bit higher, 1.6. Remember that the usual amount in a supplement of riboflavin is 100 milligrams. But again, if you remember that this is a water-soluble vitamin, it's not that dangerous because the excess you just spit out. Sorry, you eliminate it in the urine. That wasn't very professional. It's weird when you record lectures without people because I'm in my house right now, so I feel like I can say anything, but this is actually a class, so pee it out, no. Eliminate it in the urine. So the rationale for the recommended intake is based on clinical signs of deficiency and the activity of erythrocyte glutathione reductase. What is the main type of riboflavin deficiency? It's called riboflavinosis. And the thing is that it rarely occurs in isolation. When someone has a deficiency of riboflavin, it usually also has deficiencies of other vitamins. So it's usually accompanied by other deficiencies. There's been some symptoms that have been characterized, and the symptoms appear after 4 months of low intake. There are different reasons why someone might have a low intake or a low absorption of riboflavin. It could be due to anorexia nervosa, people with prolonged fasting, people with malabsorption syndromes, with short bowel syndrome, people with an uncontrolled celiac disease, or people with severe alcoholism because it alters absorption and metabolism. There are different reasons, and the symptoms are of riboflavinosis. It's first chelosis, that is lesions in the corner of the mouth, like these ones or these ones. Glossitis, that is an inflammation of the tongue. Dermatitis, redness and inflammation of the mouth, and nerve dysfunction. Most of these things, you can see them as clinical presentations in patients. So similar to what I just said, who's at risk? Individuals with cancer because of their limited dietary intake, people with alcoholism because of the decreased food, because they eat less and they absorb less and they excrete more through the kidneys. Also, people with thyroid disease, apparently people with hypothyroidism can't successfully or make enough of the coenzyme form. Elderly people may also have a decreased absorption and intake, and women who are taking oral contraceptives. There's not a clear reason why females on oral contraceptives might have some signs of deficiency of vitamin B2, but it's something important to keep in mind. So the normal intake is between 1.1 and 1.3 milligrams a day, and because this is a water-soluble vitamin, there's not an established tolerable upper limit or intake, because the excess you can just eliminate it through the urine. There's been some clinical trials using very large oral doses of riboflavin up to 400 milligrams. Remember, normal intake 1.1, up to 400 milligrams a day in healthy adults, and it has not been associated with any toxicity symptoms. In fact, high doses of riboflavin have been used to treat migraines. And that's why we have this information from these trials, because these trials were testing the if high doses of riboflavin work in people with migraines. So migraines, approximately 10% of people experience migraines. Women are more affected than men, and those who experience migraines are more likely to have allergies, asthma, hypertension, and depression. And migraine prophylaxis is recommended for people who experience more than 2 migraines a month. So that's why riboflavin might be useful in this case, because the idea, or one of the possible mechanisms of migraines, is because there's an impairment of brain oxidative energy metabolism. And we already discussed how riboflavin and its coenzymes play a crucial role in oxidative mechanisms in general. However, the cause of migraines is not well understood. That's just one hypothesis. So, these clinical trials show that after supplementing with 400 milligrams of riboflavin for a month, they saw that the frequency of migraines decreased by 50%. And it also decreased the duration of migraines attacks. So, what are the general benefits of treating someone with migraines with high doses of riboflavin? First of all, the less use of anti-migraine drugs, and a lot of anti-migraine drugs have some important side effects. Also, there hasn't been any toxicity symptoms for these high doses of riboflavin because, again, it's a water-soluble vitamin, and it is also very inexpensive. So basically that is it, the information about riboflavin. We already discussed about vitamin C and thiamine in the beginning of this lecture. And now the mini review for riboflavin. It's mainly found in meats, dairy, eggs, and some fortified grains. The function is, of course, the function of these coenzymes or flavoproteins that are oxidizing agents. The deficiency is ariboflavinosis, and there is no established toxicity because it is a water-soluble vitamin. So I hope that this lecture was somewhat clear. If you have any questions or any comments or any doubts, you can just, if there's not a specific place to address them, you can email them to me to cienf2@uic.edu. That's my email, and I will be happy to answer them. So I have low battery, probably you will see that, I'm sorry. And thank you